Hello, Professor. In this project, we are using CNN to detect image class. The group members of the projects are Ajay Narayanan Sridhar, Nandinee Kaushik, Srijit Mukherjee, and Shurit Das. So the goal of the project is to use a pre-trained CNN, which is already trained by the backpropagation weights are given by the professor. And we use it on the image data set that is also provided by the professor. We apply CNN on it. And we buy forward movement, and we use a performance measure of confusion matrix, since it's a classification problem, to understand what is the classification error and how much accuracy is obtained. And then we use the image representation of each of the features of each of the layers that we have got to understand what they're doing, what their features are, and then also we use some outside the test data set, image, it's classified well or not. So this is the overall goal of the project, and corresponding workflow is that we first discuss the code flow of the whole project, and then we show implementation and how the code behaves. Also, the comments and documentation are added to make the easier understanding of the whole code and the project. And then the performance measure is done. Then we move to the feature extraction to understand the whole how the individual layers are behaving in the feature, as images in the corresponding project. And then we go to the final presentation and video plan that we are recording right now. So the code flow consists of the 6 steps: architecture, functions, model, main, performance, and feature extraction, and then go into the exploratory mode as coined by in the project. In the architecture functions, there are 6 functions that we have used. This is also mentioned in the project documentation. I will discuss 2 of them, and I will correspondingly show in the MATLAB code that how it's being, whether it's working fine or not. I will go to the corresponding project flow descriptions our group has made. So in this apply underscore ReLU, we are importing an in array, or we input an in array of dimension n cross m cross 3, and it gives, so apply is nothing but fx is equal to 0 if x less than equal to 0, and equal to x if x less than 0. So we are seeing the maximum of 0 and in the in array part. That's it. I mean, if it's positive, it gives back the same thing. Out array is the corresponding m cross n cross m cross d array. The second one is the normalize, where we are discussing the corresponding same function where we're normalizing the entire vector. So let me show the implementation of ReLU here. So in the ReLU, if you can observe, we're generating a random 2 cross 2 cross 1 matrix in the range -5 to 5, and we are getting the output. This, if positive part is returning the same value and the negative part is returning 0, as function describes. You can also see this in the code. And then the corresponding apply normalize, we're normalizing the vector. So we are importing the n cross m cross 3, and we are converting to double, and then we dividing by the range equivalent to a range, and essentially it's coming out our value between 0.5 minus 0.5 to 0.5. And the example in MATLAB is shown here. We have taken zeros, 1 cross 1 cross 2 0 matrix, and you can see that it's turning out to be between -5 and 0.5. It can be found in the corresponding codes also. Thank you. I will hand over the next part of the discussion to my other project mates. Thank you.
Starting with max pool, the input array values to be 2n cross 2n cross d, and the output array is given a value that is lesser than the final output. That's why we're multiplying it by -1 into infinity for all the 3 n, m, and d lines. And then we start with the channel going from 1 to d, and we go row-wise 1 to 2, and then column-wise 1 to 2, with 1 cross 1, comma 1. And then the step size is taken as 2 in I and j. And then we separate out the 2 cross 2 matrix in a way in which the first element of each is taken, 1 comma 1 or 1 comma 3, and then 3 comma 1 and 3 comma 3 is taken. It becomes 2 cross 2 matrix, and the maximum value of this is taken and put in the position where it should be. Continuing to softmax. The softmax is applied exactly according to the formula that was provided to us. So the input array has 1 cross 1 cross d dimension, as so is the out array. We take the alpha to be the maximum value of the in array, and the denominator is, as you can see, the summation of the exponential of the in array minus alpha in the third column, k. Out array is basically the numerator being exponential of in array minus alpha, being element-wise divided by the summation. That was softmax, and involved we see 3 inputs: in array, filter bank, and bias values. So the size of the in array is stated, and then the filter bank, the number of filters is assigned in the code. The out array is given zeros in n, m, and d2. Then we go row wise from 1 to d2, column wise from 1 to d1, And then we see a star product being taken of the image and the filter, and the output is finally added with the bias values. Here are the outputs for the convolve, apply convolve. Here are the values that we get for the softmax. And finally, we see the maximum value when we do max pool, 0.99. Thank you.
Hello and welcome, Professor, as well as all the others who are viewing this video. My name is Shurit Das, and I'll be going through one of the functions used in this code, which is named fully connect, as well as the main parts of a code, which encompasses all the other things together so that we can call all the other functions and make this as concise as possible. I'll be starting with fully connect, and before that, I would like to share my screen and show you how the algorithm functions with the help of flowchart. Simply put together, it simply takes in an array of size m cross z1, and then we normally multiply it to a set of filters. Okay, so which is also known as a filter bank. There are d2 filters, and each is of size m cross d1. After multiplying this to the array, we add a set of d2 bias values, which exactly results in d2 scalars. This is basically converting all the pixels into an image. Like, we input an image to the neural network, right? And for each image, we get one scalar value, which will in turn help us develop the probability of that image falling into a certain classification. Okay, let's just move into MATLAB and see the code which is required for fully connect, accepts three parameters, the in array, the filter bank, as well as the bias values. So we're considering only the number of filter banks here. We don't need to know any of the other dimensions. So we fetch just the value d2 from the size of filter bank, and we initialize it by zeros by setting it to a 3D matrix where the number of rows and number of columns are one respectively, and the number, third dimension is d2. We iterate over all the d2 filter banks, and what we do is that we simply multiply the in array with the filters, and we add them all up, and finally we add the bias values. So we have designed a class for everything, and all the objects of this class are used to monitor and adjust and specify everything that is happening inside the code. So let's just move into the code. You'll have a brief view of the model if you look here in the flowchart. Basically, this is a child class named model, and this is the parent class handle. So basically, model inherits everything from handle. Okay, and there are basically two attributes: the properties and methods. Okay, so the properties hold everything that has been specified in the project documentation. We have to, the main file which has to be imported. This is CNN parameters.mat, which has all the important things that's required by the code to process the information. We have different layer types, I believe six. Fully connect is one of them. We have the filter banks, which is used for convoluting and other things. There are the bias vectors, which has to be added after multiplying with the filter banks, and there obviously are the layer results. So the layer results are the output of every layer. Basically, we put an image and make it pass through every layer type, and after it passes through each of the layers, the results are stored in layer results. Let's just move into methods, and we just describe a function known as model. This is the main function. Okay, and we create an object, and we assign layer types, filter banks, and bias vectors to an object. This is the forward propagation. This is how we propagate the input images through the neural network. And if you see this part, it's actually very simple. We're just running a for loop. It's an iterative loop. So it's the length of object.layer type. So basically, we know that there are 18 layers, right? So as a description, so 1 to 18, D goes from 1 to 18. For each iteration, it compares the name of the layer with all possible set of layers mentioned in the project description. It can be IM normalized, it can be convol, ReLU, softmax, max pool, and fully connect. Once it gets a match, it just calls the respective function, and for each iteration we've stored the result in object dot layer results. Okay, so D is the number of iteration, and finally after the 18 layers, the final output is stored in output arg. So this can be expressed as the object.layer results for d is equal to 18. So this is the output after the 18th layer. Great, then let's just move into main. And as I've just mentioned here, it's a CNN model weight verification performance testing. So we load cipher test data.mat, and we load debugging test.mat just to see if our results are, this has been just provided for having a sanity check if our code is working as it is supposed to work. Okay, so we take a random image called IMRGB. This is what it looks like. Okay, then we import the model that I just mentioned to you. The star explains that all of the things of the model have been imported. Okay, we store the model in a variable called m, and then we call the forward propagation function of m. After this, we basically go through all the layers and sort the layer results, and basically compares all the things, all the parameters, if we've been right through all the steps, using the debugging test.mat file to understand if the things are in correspondence to the real world and we're not just frantically writing code to get the thing done. Okay, so you can see all the results here. And next, one of the most important things is that finding the most probable class based on debugging data. Okay, so what do we do here? So we basically find the maximum probability classification and we assert that image to that class essentially. Okay, so check the performance. To develop a metric of the performance, we call the confusion matrix. This is the function. This is a very small function. We'll just call confusion matrix and we put in the true labels and the predicted labels. We find the accuracy by computing the number of truly classified images to the total number of images. Diagonal elements are the right classifications. It's like 1 falling into 1, 2 falling into 2, 3 falling into 3, or 4 categorized as 4. And all the other elements, this one has looks like 1 categorized as 2, 1 categorized as 3, or 2 categorized as 1, 2 categorized as 3, so and so on. So these are the wrong classifications. Diagonal elements are the right classifications. Okay, so we also have the accuracy here. It's 0.4371 or 43.71%. This might be a bit low because we have already received the trained weights for every image, what's the maximum probability of falling into one specific class. We convert that to a label and we squeeze it so that we can get rid of one of the extra dimensions, and we finally provide the class, and that's it. We basically need to show this for one specific image, and that's what we have done in display layer results. Okay, just loaded a random truck image just to see if our model is working perfectly or not, and then this is the image. Okay, we forward propagated. And so what we've done is that there's a lot of redundancy in the layers. Different layers have been called different number of times. So what we do is that we have stopped at very crucial parts of the program so that we can show you how the functioning has been done. That we have stopped at the beginning of the first layer where we normalize it. Okay, you get the result. And then you go to the second layer, which is convolution. This has been one convolution out of the many convolutions. This is what. Then we have, shown how the ReLU works. All the negative values to zeros and all the non-negative values will remain as they were. And then we move into max pool. We see how max pool works. It basically downsamples the image. That was layer 6 though. And then we move into softmax. It's just converting things into probabilities, right? So we have used a bar chart to show that the image of what we had given had been classified into different categories by different probabilities, and the truck has the highest probability. So hence being expressed as a truck. Our model considers the image to be a truck, and that's about it. I'll ask my partner to move on with this.
Now we'll visualize how an image output looks after passing through each and every layer of a CNN. Let's get to the. So here we're just loading ZIP-10 data, and then we're loading a random truck image. And after loading it, you can see the image being displayed over here. And we'll load the model and then run the forward function or the forward pass on our input image RGB. And after running that, we visualize each and every results and each and every layer results. So here we are visualizing layer results after normalization. And you can see this is the layer results after normalization because it's getting to -0.5 to 0.5. And we're also visualizing the results after convolution. Note that we're just visualizing the first channel. The first channel output looks like this, and we're also visualizing in grayscale. And similarly, we also output the visualization after passing through ReLU. Visualize max pool. You can see a similar high activation on the truck shape. You can see the activation follows the shape of the truck and the softmax function. And you can see that there's a high probability for being truck, and the next one is being ship and airplane. You can see that automobiles and is all very close, and living animals have really low probability. Observing the output model classification when we pass a random image from an internet, and we'll also pass a few of our teammates' images and see what happens. We also suggest one method to handle unknown categories. Okay, we're just loading out the data set again in order to get the class tables. We'll be doing the same thing for a random truck image that we got it from the internet. We also note that the estimated class is truck and it has a probability of 0.33. And we also run the CNN model in our teammates. Nandinee will be the first. We just load her picture and we resize similarly to 32x32, and then we run it. You can notice that the output is coming up as ship. I believe this is because there's like water in the image, and the model is trying to identify the water and saying that it's close, it's being a ship. And over here, we pass on to the next group mate. That's Srijit. We load a picture of him, and we also do something similar to resizing. And we notice that his estimated class is actually cat. To propose an approach for how to handle unknown category. So we're going to keep a threshold value. If the probability of the maximum class is greater than the threshold value, we say that the output corresponds to the class that corresponds to the probability P. Else we just say the output corresponds to the label unknown. Thank you.